So we're now ready to turn our attention to one of the key transforming operators in the Flux class. Earlier we talked about the map transforming operator. Now we're going to talk about the flatMap transforming operator. And as you might expect from the name, it's going to be used to transform the values or the types that are emitted by a flux. This lesson will also describe how Project Reactor's flatMap can be used to do concurrent processing. It's super duper cool. So the flatMap operator transforms the elements that are emitted by the flux asynchronously. If you recall the map operator, it transformed things synchronously. And the elements that are emitted into something called inner publishers, which sounds a little bit mysterious, and it's actually really super cool. Basically, each input element, T, is mapped to a publisher, R. So you can change the types if you so choose. That publisher will emit one or more items. And this gets into one of the key things that's important about flatMap. Unlike map, where it's a one-to-one input and output, flatMap can be one to many or many to one or whatever. You can get much more flexibility. The inner publishers that are emitted are then flattened into a single flux via merging. And this should sound very familiar to you because it's very much like what flatMap does in Java streams. Now, one of the consequences of this is that they can interleave, and this is especially going to be true when we do concurrent processing. So it's not necessarily that they're all going to be kind of concatenated together in some way, and we're going to see an example of this in a second. Another consequence, as we just mentioned, is that the number of output elements may differ from the number of input elements. You could have the same number, you could have more, you could have less. It all depends on what these inner publishers decide to do. flatMap, like map, can also transform the values or the types of the elements that it processes. flatMap is used for various things. You can use it just for good old flattening, the way we do in Java streams, but it's also used for something that's not easily done with Java streams, which is concurrent processing. So if you recall, the flatMap operation in Java streams did not support concurrency, which was really annoying, but the flatMap operator in Project Reactor does support concurrency. It's super really cool. So this particular example, as we'll see in a minute, is going to return a flux to a multiplied big fraction by using the Project Reactor flatMap concurrency idiom. And we'll walk through this both in a second and in just a short way, and then we'll take a deeper look at this when we get into the case study walkthrough in a minute. RxJava has a flatMap operation that works just like the flatMap operation in Project Reactor. Gee, no surprise there, obviously. And it's similar to the flatMap operator in Java streams, with the caveat that the flatMap operator in Java streams doesn't handle concurrency. So you can see here, this is just a simple example showing how Java streams works. We have two lists of strings, and then we go ahead and we use the of factory method operator on a stream to create a stream of lists of strings. And then we use flatMap for streams to flatten that into a stream of strings, which we then sort and print. So that's a sort of a canonical example of how to use flatMap in Java streams. You'll see again that Project Reactor's flatMap could be used this way, but it's often used for concurrency. And I typically use it almost exclusively for concurrency. One of the consequences of flatMap that we discussed briefly, but we'll talk about here a bit more, is it doesn't guarantee the order of the items in the resulting stream, so they may come out of order. If you want things ordered, then you should use, excuse me, the concatmap operation or operator. So let's talk about the Project Reactor flatMap concurrency idiom, because it's really super cool. So we often use flatMap when we want the items that are emitted by the stream, or each item that's emitted by the stream, to be applied in its own threading operator or its own threading context, like a thread pool. And this may be useful for things that we're talking about earlier before the class. So here's a simple example. This is known as the flatMap concurrency idiom. Here's a simple example. We start out with taking a big fraction list and turning it into a flux by using the from iterable factor method. So we now have a flux. This is still sequential, but it's a flux of big fractions. And then we use flatMap. And what flatMap is going to do, here's the way to think about this. flatMap basically says, for each big fraction BF in the stream that we're processing, go ahead and apply the various actions in this mono chain that you see off to the right. So what we do is we go ahead and we say, take the big fraction BF, right? So we have for each big fraction BF, take BF and use from callable, subscribe to run each of these calls in a thread in the common, in a parallel thread pool, and map each of those big fractions BF in a separate thread or in a thread in the parallel thread pool, and have it multiply by some big fraction constant. So what this is basically doing is it's saying, for each of these things, go ahead and use threads in the parallel thread pool to do the multiplication in parallel. So with just a very small amount of code, you can get a lot of things to go at the same time. And then when it's all done, I guess I walked through this one step at a time. So for each big fraction, emit it as into the inner publisher, subscribe that to run in the parallel thread pool, and then perform the multiplication. And when everything is done, when all the computations are done, whichever thread is the last one to come through in here and do the multiplication will then go and do the reduction. In this particular case, we're going to go ahead and add up all of those values that were in that multiplied stream that finished in parallel. We're going to add them all together, and that'll be the result that comes out of reduce. And we'll take a closer look at this when we get to the walkthrough of the case study. It's also worth comparing flatMap and map. The map operation transforms each value in a Flux stream into a single value, so it's a one-to-one mapping, and it's intended for kind of synchronous, non-blocking one-to-one transformations. See here, literally you can see one-to-one transformations there. In contrast, flatMap transforms each value in a Flux stream into an arbitrary number, 0 or more values. And it's intended for asynchronous, often non-blocking 1 to n transformation. So you can see that you can have a bunch of things come in, and you can apply transforms, and you can get the results. They could interleave, blah, blah, blah. So you could get more stuff out with flatMap, and we'll see some examples of that here shortly. You could also use it for one-to-one transformations. For example, the thing we just saw with the flatMap concurrency at M was indeed a one-to-one transformation. We were just doing everything in parallel. But you can also get things to be flattened as well. So that's the end of the overview of the flatMap operator in RxJava. It's very, very powerful.